So you guys can probably hear I'm starting to lose some voice here. So we're just going to try to get through the rest of 15.1 here today. So we started 15.1 last time. Just going to review a couple of concepts from 15.1. So one of the things we talked about in 15.1 was that we started talking about exponential functions. And we talked about how there was two different, thank you, Cameron, here it is. There are two different ways to represent an exponential function, right? You can write them as a times b to the x, and then a times e to the k x, right? And then amongst all exponential functions, you have two types. You have growth and decay. So if we're in the form f of x equals a times b to the x, we can identify it as growth if the a is greater than 0 and the b is also greater than 0. I'm sorry, greater than 1. Or if a is less than 0 and then b is between 0 and 1. So for example, like y equals 2 times 3 to the x would be growth. And then y equals negative 2 times 1/3 to the x would also be growth. I know, me too. Similarly, for decay, if a is positive, then b has to be between 0 and 1. Or if a is negative, then b has to be greater than 1. So again, for example, y equals 2 times 1/3 to the x would be decay, as would y equals negative 2 times 3 to the x. Is everybody kind of okay there? Where like each example kind of correlates to the situation? You guys see that? Okay, if we're in the other form, we're growth if a is greater than 0 and k is greater than 0. Or if a is less than 0 and k is less than 0. And then it's decay if a is greater than 0 and k is less than 0, or if a is less than 0 and then k is greater than 0. And again, oh, that's embarrassing. I hate that too. Well, it's because you're goofing around and not doing your work. Hi, Reese. What's up?
Ava has my tablet.
Oh.
I told you I got this out my tablet. I didn't ask you. I want to switch out.
So this is something where you can use these criteria to identify whether an exponential function is growth or decay just by looking at the equation, right? Sounds like a potential homework quiz question to me. is, can you use those criteria to identify if something is growth or decay, or list the criteria for growth or decay? Another problem that we saw last time was writing the exponential equation from like a table of data. Now we saw that this was really easy. If one of my points has a 0 for x, so what we're trying to do is write an equation y equals a times b to the x. So if we have x equals 0, we can plug that in for that point for the x and y. And what is b to the 0 equal to? 1, right? Remember that anything to the 0 power is 1. So we're just left with a equals 1. So if we then start over, but this time use a different point, say the point 1, 2, we can use that along with the fact that we now know a is 1 to solve for b. So we'd have our answer. There's our equation. Or if we wanted to, we could simplify that down, because I know any number times 1 is just itself. So that could just become 2 to the x. You don't need the 1 times in front. It's not wrong if you leave it there. But that would be like our final answer. So that's kind of a review of some of the important stuff that we did last time. Today we're gonna, go ahead. Look at some story problem examples. So this first situation says, given the population of a certain city in 1990 is 782,000 and change, and the population of the same city in 2000 is 895,000 and change, and assuming the population growth is exponential, in what year will the population reach 1 million people? So this problem really has 2 steps to it. Step 1, we need to write our exponential equation. And then step 2, we need to solve that equation. Is everybody okay there? So when I look at this, I see 2 variables, right? I see one of the variables is like the year, and the other is population. Does that make sense to you guys? I'm reading the question through. Which one of those should be the independent variable and which should be the dependent? Which one depends on the other? Population depends on year, right? Good. So I'm going to use the letter T to represent year or time, and then the letter P to represent population. So if I do that, I would have 2 points, right? The first point would be 1990, comma 782,248. And the other would be 2000, comma 895,193. Everybody feel okay there? What's the unfortunate thing here, though? None of my x's are 0, right? Boy, this problem would be a lot easier if they were. You know what I'm going to do? I'm going to make it so that one of my x's is 0. So instead of t being equal to years, I'm going to say t is equal to the years since 1990. I'm going to leave p still to be population. If I do that, then I'd have 0, 782,248, and then 10, 895,193. Is everybody cool with the trick that I just pulled there? So because that value, x coordinate is 0, I know that its y coordinate is just going to be my value for a. So if I use the other point, and I fill this in, I know the a and I know an x and y, so that gives me an equation I can use to solve for b. So far, so good? What do I need to do to solve for b then? What do you guys think? Divide both sides by 782,000 and change, right? Okay. What do I need to do next? To solve for b. What needs to get canceled out next? The exponent of 10. Great. What operation is going to cancel out that exponent of 10? Well, not a square root. That'll cancel out an exponent of 2. A 10th root. Very good. So just do a 10th root to both sides. Now, because that's an even root, 10 is an even number, what also do we need? Plus or minus. So we still need a plus or minus. Now, I could type that into my calculator, but I'm not going to because I'm just going to leave it so that I have an exact answer later on. But remember, what do we know about the b in our exponential equation? Can that be any value? Oh, what kind of values are restricted? Negatives. So specifically, we can drop the plus or minus there, just the plus. So our equation then is going to be y equals 782,248 times the 10th root of 895,193 over 782,248 to the x. That's like the end of step 1. Everybody feel okay there? Well, actually, let's write it this way. I really mean P of t and t, right? Now, step 2, we want to solve $1 million is equal to P of t. Remember, the question was asking us, in what year will the population reach 1 million? So we're solving P of t equal to 1 million. Now, what that really means is that we have like yes, sure. We have that, right? Now, currently, we do not have the algebraic methods developed to solve this algebraically, but that's okay. We do have a tool that will be able to solve any equation for us, whether we know how to do the algebra or not. What is that tool? Our graphing calculator. How are we going to solve this equation? We're going to graph both sides of the equation and find the intersection, right? So we'll take out our graphing calculator. So into y1, I'm going to type in the left-hand side. So 7, 8, 2, 2, 4, 8 times. Now, do you guys know how to get a 10th root into your calculator? So the way to do that is you type the number 10, and then you press the math button and pick command 5. And there's your 10th root. And then I'll make my fraction. And then I'll have to the x. And the other side is going to be 1, or the y2 is going to be 1 million. So far, so good? All right, so before I hit graph now, I want to sort out my window. Remember, my x's are representing the time, that's the year since 1990. So it took 10 years to go from 782 to 895. That was about 100,000 people we gained. My suspicion is in another 10 years, we'll be somewhere right around 1 million, right? So I'm going to overestimate that and say we'll go out to 30. I'd rather overshoot it than undershoot it, because I don't want to have to go back in and monkey around with the window. And then let's think about the y values. The y's are the population, right? The smallest my population's ever going to be is here at year 0 at 782. I'm not typing all those specific numbers in there. I'll just round down to a relatively even number like 750. And then the biggest my y needs to be, well, I don't know what that's going to be, but I know it needs to be bigger than 1 million because I have to see the intersection. So maybe I'll do 1.25 million. Everybody feel okay there? So that should be all set. Let's hit graph. So here comes my exponential curve here. Looks rather like a straight line, not very curvy, but that's okay. And there's my line for 1 million. So second trace, intersect command. Because there's only 2 curves in one intersection, I can just press enter 3 times. So my answer is T is about 18.2. Now, does 18.2 answer the question? Let's go back and read what the question was actually asking us. In what year will the population reach 1 million people? Well, that doesn't really do it. Remind ourselves that T is the years since 1990. So this really means 18.2 years since 1990. So during what year? Yeah. Everybody feel okay with how we answered that? Yes. Now, what happens if the question instead was phrased as at the start of which year will the population reach 1 million people? Should we be rounding that 18.2 up to 19 or down to 18? Be careful here because it's at the start of what year? If I round it down at the start of 2008, are we going to have 1 million people? No, right? We're going to be over here below the 1 million line. We need to round up. So depending on the phrasing of the question, we may have to round differently, right? So notice even though it's 18.2, I still rounded up to 19 because of the way the question was phrased, right? Now, there's one little problem with what we did here. So if I wanted to, I could use that model that we had just made to predict what the population would be in, say, like 200 years or something, right? Or 1,000 years. Everybody agree? So let's say we did that. So if I wanted to know what the population of this city would be in 1,000 years, I plug it in, and oh dear Lord, look at what I get. 5.6 times 10 to the 11th. That's like more people than there are on Earth right now in one city. That doesn't seem possible. Do you agree? Something's up here. Well, here's the issue. Is we assumed here that the growth was exponential. Is that a realistic model for population? No, right? At some point the population is just going to its growth is going to peter off because you've run out of space or run out of resources or other competitors have come in and are starting to knock off the population faster than it can be replaced. If your population gets too dense, diseases are much more likely to pop up and really drive down your population growth. Everybody agree with that? So really what we'd like is a function that grows exponentially when things are small, but then starts slowing down and stops growing when things approach, some ceiling. Can you guys think of any other real world things that kind of you'd expect to grow that way?
When you're pushing the squares, they increase by 4 minutes. And then it's start off at 4 and then it goes to 8 and 6.
Mm-hmm. So that's exponential growth, right? But it's not slowing down. What do you guys think? Can you think of anything that in the real world that when you start, things go really fast, but as you do more and more and more, eventually it starts slowing down?
Dogs age. Because dogs, they age really fast and slow down. It's perfect thing for humans. It's slowly aging.
So like growth, then like physical maturity, right? That happens very fast and then slows down. Like once you've reached your adult height or weight, like not much changes.
And the dog will reach its adult size by 1 or 2.
Mm-hmm.
And it takes
Yep, for sure. But even humans for their lifespan still kind of functions the same way. You grow a lot more early on, and then that slows down dramatically as you get older. Yes, sure. So some other examples might be, like the economy. Like if you create a business, typically you make a lot of money right away when you don't have a lot of competitors. And as that marketplace begins to fill and your goods and services, or the good or service that you're providing is reached more and more customers, it's harder and harder and harder to continue to grow your business. That business growth slows way down. Or natural resource extraction. In the beginning, it's easy to get the natural resources out of the ground. The more you take, though, the harder you have to work to get it out. Or human performance. Like if you're in the weight room lifting weights, you get stronger really fast initially, but once you've gotten strong, it really takes a lot of work to continue to get stronger, right? Or faster or whatever, make the substitution, right?
You're morbidly obese. Once you start working out and losing weight, you lose a lot really fast. It takes forever to lose it.
Mm-hmm. Yeah, for sure. I think weight loss in general works that way. It doesn't continue. So what we'd like then is another model that'll behave this way that we can use to describe these situations in a more realistic fashion. So that other model is called the logistic function. So a logistic function is just something of the form like this. Notice that in the denominator, as part of the denominator, you have that exponential function and the two different ways of writing that. So A, B, C, and K are just like positive constants. When B is less than 1 or K greater than 0, that's going to be logistic growth. And when it's B is greater than 1 or K is less than 0, that's a logistic decay. And this is really cool because your logistic function always has 2 horizontal asymptotes. So one of your asymptotes is always y equals 0. And the other depends on the function. It's just going to be y equals c, where the c we're talking about is, the numerator there. And then depending on if you're talking about growth or decay, you're going to get this like S-shaped curve. Let me try doing that again. Or it kind of looks like a stretched out S. That's an example of logistic growth. But you see here where it's growing really fast in the beginning and then slowing down towards the end.
That's good.
See you later. So again, this value for C, we call the limit to growth, or you could call it the carrying capacity. That's often specific to population, referring it to that way. You might have heard discussions about like the carrying capacity for the Earth being, some billions of people. You guys feel okay with what we've described here? Now this seems like a much better fit for the situations that we just discussed, right? So let's do just a couple of basic examples, computational examples. So it says, graph the following function on your calculator, find the y-intercepts in the equation for the horizontal asymptotes. So we don't really need our calculator to do this question. So we'll do part A just by hand, and then we'll graph the other one. So to find the y-intercepts, how do I do that? We're just talking about it in the last chapter. We're not setting the denominator and numerators to 0. You want to plug 0 in for x. So you're just plugging 0 in for x. We're not solving anything. Now, what is 0.6 to the 0 equal to? Nope. 1. So my denominator just becomes 1 plus 3, so that's 4. And 10 divided by 4 is 2.5. So there's my y-intercept, the 0.0, 2.5. Feel good there? My horizontal asymptotes, 1 is easy because it's the same for every logistic function. Y equals 0. And the other one is y equals c. What's the c value here? 10. Just the number in the numerator. Everybody feel okay there? So again, did not need my calculator to do that, although I could have used it. I'm going to type in equation B here and just show you on the calculator what the graph would look like. Oops. Hold on, I missed the 4 there out front. Okay. And I'm going to reset my window here. So I'm just going to go from -10 to 10 on the x-axis probably. And the y's, well, I know that the y's are going to go from 0 to 31. Because those should be my asymptotes, right? And then I'll just hit graph. And let's see what we get here. There we go. Pretty steep, but looks like that S shape. And if I wanted to, then I could do like second trace and pick the value command. and just pick 0 for x, and there it is, 31 over 5. That's my y-intercept. You guys feel okay here? One more example and we're done here for today. Yay! This says the population of a city can be modeled using the logistic growth equation, P of t equals yada yada yada, where P is the population in the city T years after 1950. Look at this. They did that same trick that we used on the previous problem. That's nice. At the beginning of what year will the city have 1 million people? So this sounds a lot like that first problem, right? But this is only one step. Why is it going to only be one step? Because they gave me the model already. I don't have to write my own model. It's given to me in the problem. Sweet. Mr. Kulik, will I ever have to write a logistic growth equation? Nope. You will not. So really here, my problem just becomes solving P of t equals 1 million. Again, do I have the algebraic skills necessary to solve this by hand? Not yet. What are we going to do? Type it in the calculator and find the intersection. So I'm just going to start on that. 525. 397 1 plus 21.783 times e to the negative 0.04982t, and then 1 million. Everybody okay with how I've gotten this into the calculator so far? So now I'm going to set my window. Again, we're talking about population and time. My x minimum should probably just be 0, right? Now, I have no idea what the initial population was. I mean, I could compute it, I guess, if I really wanted to by plugging 0 in for t. But I'm just going to take a guess as to how many years after 1950 before this thing hits 1 million people. I don't know, like 100 years or something? Just giving it a guess. Now for my y's, I'm going to use my two asymptotes, right? So one asymptote is y equals 0. So that looks good. My second y asymptote, or horizontal asymptote, is y equals 1,425,397. Yuckarooskies, that's too many different numbers to type in. I'm just going to type in 1.5 million. And then I'm just going to hit graph and take a look here. So there's my logistic curve. There's my line for 1 million. Sweet. Second trace, intersect command, enter, enter, enter. And I get 79.001. And then remember, this is years after 1950. But what is the question actually asking for? Beginning of what year? Should I be rounding up or not? Down? Up. Yeah, so t rounds up to 80. And then if I add that to 1950, I get the beginning of the year 2030. even though it was 79.001, still needed to be rounded all the way up to 2030. And that's it for today. What do you guys think? Cool. Not bad. Next time we'll do 15.2. That's just like more kind of story problem application like we're doing here, just with exponential. We'll talk about a couple of specific models that we will use, but in general, it's just going to be like story problem examples, doing kind of the same thing we've been doing here, graphing on the calculator and finding intersections. So the hard part is just getting the setup, and the calculator takes care of all the heavy algebra lifting for us. And then we'll start transitioning into logarithms, and then we'll eventually end up into solving, and then we'll do some financial stuff. So that's kind of where things are heading from here. But I'm going to stop talking because my throat is not feeling great.
Can I go to the bathroom?
Yes.